Hi there, guys. My name's Tim Darby. I'm with Sony Computer Entertainment Europe, and I'm going to be talking a little bit about rebuilding Killzone servers. Just a tiny bit about myself. I'm a senior server engineer with Sony's online technology group. We provide help to the game teams implementing online features to Sony's first-party games. I've been working with Guerrilla Games on various of the Killzone titles on and off ever since the first Killzone game in 2004. Most recently, I've been working with Guerrilla Cambridge on Killzone Mercenary for the PlayStation Vita. So what am I going to be talking about today? Well, as I say, it's rebuilding Killzone servers. So I'm going to be talking a bit about how we originally built the server set for Killzone 1 way back in 2004 on a PS2, and then how we grew our server architecture as we added features and iterated through on that title. And then I'm going to be talking about how we rebuilt the whole set on Amazon for the latest set of titles in the Killzone franchise, and how we made use of Amazon services to kind of get more bang for our buck, to be able to react and change and be more dynamic and flexible in how we did things. I'm going to be talking a bit in detail on how we used those AWS services for specific use cases, and then finishing up with a few of the issues we had and lessons learned, and hopefully a couple of minutes for Q&A. I've fueled myself up with plenty of coffee before this session to try and get through this quickly, so we've got some Q&A time though. So first of all though, what is Killzone? To help with this, I've just got a short video. So, yeah, obviously Killzone is a first-person shooter. It's a PlayStation exclusive franchise, and we've been going through iterations on the title all the way back since 2004. So, Killzone servers, the history of them starts way back on the PS2. We started out on Killzone 1 on the PlayStation 2, really just serving the core multiplayer experience, getting people into games, playing, and finding a new game after that. So quite a straightforward experience back in their day, and just really using the minimum server backend to be able to give that good experience with client-server networking. And this is pre the Amazon days for us. The architecture we used, really, it's consisted of using our hosting facilities that Sony had in the different regions with groups of real-time game servers that were deployed. It was all centrally written technology and nothing actually specific to the Killzone title in that back end. So we used this tech stack on several games, including Killzone, and there was just a little bit of configuration. So we had multiple game servers in each region so that you got low latency connection for playing your real-time game, and then a centralized server stack in one region providing login, lobbies, and then you go into the lobbies and you find a game and play it. limited in terms of the amount of persistent data that we stored. We had a rocking 256 bytes of data for each user's profile stored in the DB backend. And actually the storage for where all the players were, what the current servers were that were actually connected to the system, that was all stored in this one central management server that was a rather critical point of failure, because if that server fell over, you had to restart the whole set for everything to be picked up again, which meant you'd have all your users kicked out of their games, which was less than ideal. Moving on from there, a couple of years on, now at Killzone Liberation on the PSP, well, by this time we wanted to actually have a bit more of a persistent experience. So the Online Tech Group took on a server stack that was actually written by the San Diego studios for some sports games originally, and brought that in as a shared technology stack that was used by Killzone amongst other games. And that was a very classic kind of three-tier architecture. You got the presentation tier servers behind a hardware load balancer, and they're running Tomcat, providing customized JSP for each title, providing game-specific markup that the game uses to show its leaderboards, all the community features, profiles, medals and badges, that kind of thing. So that provided all the online game screens. Beneath that presentation tier, we had the kind of business tier being accessed via Java RMI, and that was just kind of Java standalone apps. And those two top-tier servers were running sessionless, and they weren't in what I would actually really call a cluster, because there was no cross-cluster communication at all. They were running totally independent, and all of the orchestration is done down in the database layer through a connection using JDBC, PL SQL calls to store procedures for all of the management of anything that needed, like I say, any kind of transactionality or orchestration. And then actually for things like score posting, they are managed through an asynchronous batch processor, where we'd use one of the database tables as a queue and have the batch processing server sat there constantly checking for things to come in. So that would be dealing with posting scores, putting them into game history, pushing them into leaderboards, and updating anything that needed to be done as any kind of scheduled tasks as well. And things like the leaderboards were a big load on the database, because you got a system there in the SQL database, and you've got constant updates to it on a table which has got quite a lot of indexed columns for all the sorted columns on the leaderboards. But at the same time, that's being read as well. So there's a bit of a battle going on between the database for reads and database for writes there. So when we came onto Killzone 2 on the PS3, we're talking like another couple of years later on from that, 2009. Still using essentially the same real-time game server backend with the regional servers. But we'd switched over on the Java side of things to use materialized views for the leaderboard system, actually trading off latency in read access to the database views of the leaderboards, and meaning we weren't loading the kind of leaderboard table as we're reading it with the writes as well. And also there was some shared services that were implemented in that main server set that were used for features like Battle Replay, which was a real-time playback of multiplayer missions and a kind of a top-down view. And that actually started to muddy the waters up at the presentation tier then, because the presentation tier servers relied on an NFS mount to a shared file system for storing those replay files that the clients were sending up whilst they're playing multiplayer games. So as you see here, as request on, the server set has kind of accreted functionality to a certain extent. And by the time we got through in 2011 with Killzone 3, once again, we still had problems with the leaderboards. The leaderboards, even in the materialized view, MVs are actually causing more processing to go on the database, because whenever it refreshes the materialized view, there's a lot of DB activity going on. And with the reads being quite heavily done from the website for the game, we thought, well, what we'll do is we'll actually offload some of those read activities by replicating the leaderboard database tables, among other things, over to the website's DB schema, and actually transform the data at the same time into the schema that was most convenient for the website to use. Also, by this time, we'd actually we'd moved on from this old style view of the gaming side of finding a lobby, looking at the games in the lobby, trying to find a game that's not already full by the time you try and join it. And we moved over to a system where we did matchmaking. You pick your game mode and you rely on the server backend to match you to a good game. And because all the matching and the real-time game side of things was done on the C++ side of the servers, we had to actually add in another server to that real-time cluster for the matchmaking. And for the first time, we had to actually add in title-specific logic there, because it is quite specific to title. You can't just configure in the rules for whether a game has it more important to match people against the same skill versus people who are a close latency distance to you. And that system was a bit problematic even then, because the real-time game system for the matching side of things relied on pushing the request, and the client just waits and waits and eventually gets told, here's your game. So there's little feedback to the end user of what's going on during the matchmaking process. And also, that matching service was a significant bottleneck in the system, and it wasn't something that could have been easily sharded out in this case. And so when we had problems and the game team wanted to be able to see what was going on in the matchmaking server, it was quite tricky. And the act of turning up the logging levels on the matching server, that in itself could tip the matching server over the edge. And between it being written in the system, it was quite hard to debug, hard to actually see what was going on, and tricky for the game team to update, really had been getting to the breaking point of being able to use this architecture. And by this point, also, other game teams that we worked with within Sony had already moved over to their own server backends. And we'd moved from a situation where, back in 2004, none of the game teams really had their own server engineers. And by the time we got to Killzone 3, Guerrilla Games had their own pretty significant server team available to start implementing these features themselves. Brings us to 2013, which was guaranteed to be a pretty damn busy year for us. We're going to be releasing Killzone Mercenary in September, and then Killzone Shadowfall in, oh yeah, tomorrow. No pressure. On the one hand, this was actually good timing, because we had a bit of an opportunity and a bit of impetus to change how we did things. On the other hand, there's a lot of time pressure. With Killzone Mercenary on the PlayStation Vita, we had some significant departures from the functionality we wanted to provide for the game, because we're on a different platform. We're on a mobile platform, but we still wanted the offline experience to be actually integrated to your overall user profile and your kind of whole community status. With Shadowfall on the PlayStation 4, being a launch title, there was going to be significant focus on it. And also, the game team were keen to address some of the fundamental issues in the server backend that impacted what they could do on the client side of things. Also, the game team wanted to be able to actually actively work a lot more post-launch to integrate new features and actually engage with the community to give them what they want after the original launch. So we really had a lot of things that meant we wanted to make a bit of a change. And we had this old server architecture for nearly 10 years by this time. So working with Online Technology Group and Guerrilla together, we re-architected the whole server stack. We took a rather monolithic build and actually split it out from the ground up as separate shared components. So we had Maven artifacts at an API level for the kind of underlying low-level functions, leaderboards, profiles, monitoring, that kind of thing. And then implementations of those Maven components dependent on the API artifacts for different backends, so we could actually swap around backends and try things out. And then to go with that, we actually kept our game projects for Mercenary and Shadowfall independent from each other, but sharing potentially different versions of those underlying components, but also able to build their own things specific to title as well. We also moved from having a kind of an Ant-based build for the big monolithic server set over to using Maven, and from a rather custom build system for both the real-time, the C++ side of things, and also the Java side. Moved over to Jenkins for both of those components. On the C++ side that I don't actually cover here, that was a total rebuild, and we actually still kept in C++ for the real-time side, but rebuilt that from the ground up to actually reduce anywhere we could any of the latencies in the system. We also wanted to move over from a rather static kind of deployment methodology over to dynamic scaling. And this was to actually deal with a few of the issues. We wanted to try and work out any of the single points of failure from our system and actually move over to a much more generally resilient architecture. We also wanted to get away from a kind of a working practice that we got caught up in where we predict before launch what kind of concurrency, what kind of active user base we're going to have, statically build and statically load test the servers out to that, and then scramble like crazy at launch if we'd underpredicted. And if we hadn't underpredicted, if we'd overpredicted, we'd have to scramble to justify why we were spending money we didn't need to and having many servers sat idle. So we wanted to move to a much more dynamic system where the system itself would actually scale up and down with the load. And we also wanted to use AWS services. But we didn't just want to use them for the sake of using AWS, because it was kind of sexy. We wanted to use it because we wanted to spend as much of our time as possible implementing game features. You know, we're not huge teams actually working on the games, and we want to actually write game features and not actually spend all our time putting together queuing systems, building our own monitoring backends, building continuous deployment systems, all that kind of thing. We wanted to actually be implementing leaderboards and award systems and stat history graphs and all that kind of thing. And the only way we could do that is if we spent much less of our resource on the structural elements of the game servers. So, having taken those principles, what we ended up with was, first of all, Killzone Mercenary. And the back end for that actually ended up quite straightforward and simple compared to what we'd done before. The actual API used by the client, straightforward REST. You use Jersey inside the Tomcat servers that are inside a Beanstalk environment, and that used Amazon ELB for the SSL termination. That was an auto-scaled environment, so we could pick up with a load and add new servers as necessary and then scale down automatically. And within those servers that we built using Maven and used Spring for the kind of runtime configuration, we used Spring to actually add in instances of those underlying services in such a way as we could swap them out nice and easily with a quick redeploy. So we could take our leaderboard service originally on SimpleDB and actually swap it out for Dynamo during development without actually impacting the API used by the game client or actually even most of the internal APIs used by the game code. It was only a change of constructor that was needed. And then we had many of the other components mixing in use of Dynamo, S3 for things which are kind of higher latency storage but were going to be big, and then quite a lot of use of SQS. And we used CloudFormation to deploy it so that we could get away from kind of having a huge worry about whether we were going to be deploying a new server set and whether we could afford the time to spend to build up a new environment for E3 or another event like that. We wanted to be able to just quickly spin up a new environment, and then when we were done with it, just take it away quickly. We also used the same build setup for the other components of the server set. So the admin server, just the same, Beanstalk-based, sat on Amazon, using GWT to build it, because we had most of our experience on the Java side of things, and switching between Java and JavaScript for coding is a way to get serious migraines. So we kept with that same kind of build. And then the final component we had there, the scheduler, which is one place we differ from Killzone Shadowfall. That, again, straightforward, simple Beanstalk. But in that case, and actually something that's slightly wrong on that diagram, when the Amazon Beanstalk single instance type came out, we switched over for that. So we no longer were paying for an ELB that we weren't actually using within that scheduler app, but we were able to keep using the same consistent build and deployment setup that we had for everything. So unlike previously where you had a significantly different deployment step for the different parts of the app, everything was nice and straightforward and homogeneous. One thing we actually simplified for ourselves as well was that on Killzone Mercenary, rather than using our own real-time game servers, we actually use PSM functionality for that, which is why you don't see anything relating to matching, NAT traversal, peer-to-peer or client-server networking on there. So that's Mercenary. Killzone Shadowfall takes that same kind of basis and just grows it out quite a lot. Shadowfall runs with dedicated servers and actually goes to a hybrid deployment topology. We actually have, as you might guess, within Sony, we've got our own hosting facilities in a number of regions. So we have clusters of kind of statically provisioned game servers in the regions where we've got Sony for our hosting. In some of those other regions where Sony doesn't have its internal hosting facilities, we use AWS for deploying the real-time game servers. Let's say they've been rebuilt from scratch. And in the AWS regions, we use the autoscaler. So we can actually scale up on demand, and the autoscaler side of things manages resilience. So the autoscaler automatically swaps out and replaces any server instances that go bang at 3 in the morning. Also, on the Shadowfall side of things, because they wanted to address the user feedback issue on things like matchmaking, whilst they had the straight REST API at the front of it, they actually also have a comment connection that the client opens so that they can push messages down from the server. And they not only use that for things like matching progress updates, but also have the facility to do dynamic rebalancing. So they can look from the analytics side of things at a potential misbalance of a cone of fire of a weapon or magazine size, and they can actually, through the admin interface, push down a server update with the system settings stored in DynamoDB and push changes for that all the way through to the game clients so that new system setting gets applied as soon as all the people who are in-game currently finish their round. Obviously, you wouldn't want to apply it straight away partway through a round because that would be really confusing. So as you see here with Shadowfall, we started out with the same kind of basis, but then expanded out and actually added an extra level of complexity with things like the hybrid deployment, meaning that we can't just use CloudFormation on its own. We've actually got the Beanstalk and the autoscaler elements being deployed through CloudFormation, but the wrapper that generates those CloudFormation templates and pushes those when we do server updates, also doing deployments of the static elements as well. And I do hope it's not a terrible pun, but I think it is because they named the deployment framework they use for that, which is chef-based, they called it Burrito. And if that's a wrapper, well, it's DevOps for you. So that gives you a little flavor of the general architecture of the servers. But what I want to do now is talk to a few specific use cases on how we've used AWS services within that. And I'll be honest, I'm going to be slightly Killzone Mercenary-centric here because being the day before launch, I don't want to tempt fate too much. Famous last words. So one area that we had to put in there very early on for Mercenary was scheduled jobs. There are a number of things that we need to actually manage periodically, so we knew we had to have that as quite a basic part of the system, but we wanted to keep it simple. So we very early on dropped in a straight, simple scheduler web app, and to avoid a lot of the clustered scheduling issues that you get, if you look at the internals of Spring Quartz for clustered scheduling, it's quite tricky. So we just had a separate server instance, min-max one server, and all that does is run Spring Quartz with a defined job list, and whenever any of those jobs get triggered, they just push an SQS message into a scheduled jobs queue. We then have our scheduled job receiver threads sat on every one of our front-end server nodes. We actually tried out a number of different versions of that deployment setup with separate autoscaler stacks for the job processors. I even tried for a short while having those scheduled job processors all on the scheduler node as well. But we kind of knew that was going to be horrible because that was replicating the old architecture where the job scheduler was a big bottleneck in the system. But what we ended up with was putting those receivers and the job processor worker threads all on the main nodes. And that was because when we load tested it, we found that a lot of the same things that required us to scale up on the worker threads were the same things with the scaling triggers for the REST API as well. And also, by actually keeping that homogeneous blob of server that does almost everything, we also gained the opportunity to do some nice little debug things, particularly things like being able to synchronously trigger jobs in a way that we could debug them. And when you're running with a large cluster of servers and you want to debug something that goes bang halfway through a job, life gets really hard when you've got to search through 30 or 40 boxes before you can find the one that actually had the job failure. And that was how we started out. And that kind of worked in dev for a while. But then we realized we were actually tailing logs quite a lot when anything went wrong. And that was never going to fly in production. So first of all, what we did was we added wrappers around those job workers to provide CloudWatch monitoring. So we have a CloudWatch data point for each different named job that just tracks the elapsed time that the job took to run. So we can then see whether the job's actually got triggered, making sure their frequency is correct, and actually tracking if a job's starting to get outside of the bounds of what you can actually practically run the job in. Whether that's because you've not got enough provision throughput on Dynamo, or if you've got a bug somewhere in the job. And that got us a bit further, and we also added data point tracking and CloudWatch, just actually chucking up a 1 if the job threw an exception when it ran, and that was a nice straightforward alert for us. But that only got us so far, because what we actually found was that in a particular case with a leaderboard validation, that was quite a long-running job. And as we got to higher data volumes, particularly when we didn't have enough throughput configured on DynamoDB, that hourly job that we were running could take 1 hour and 10 minutes. And an unfortunate side effect of this topology we built was that the job scheduler had no idea that the job was already running and would merrily chuck another job into the queue to do the same validation task a second time. And another node would pick up that job. And so all of a sudden you'd have 2 nodes partway through a leaderboard validation job that would eat most of the read throughput on the database table. And that only got worse until you actually have all your nodes running the same job and nobody able to access the leaderboards, which wasn't a good thing. So what we then added on was a layer of distributed job management where we'd use a DynamoDB table as a whiteboard to track the status of all the running jobs in the system. And an admin view such that we could see the running status of all the jobs we got configured. We could see through that one single unified view without having to go to CloudWatch how long those jobs were taking to run. We could also provide more detailed feedback on the failure status of any jobs if they went bang during their run. And we could also manage the distributed job, so we could actually set certain jobs as being run once, so that if anywhere else in the cluster that job was running when a new copy of that job got picked up from SQS, we could actually not run a second copy of that same job, but instead just increment a flag on the Dynamo table for that whiteboard so that we could see through the admin app, oh, yeah, that job got triggered 5 times in the time it took to run. This is not a good thing. So with that, that actually gave us a nice kind of middle ground between doing complete distributed job scheduling and management, but also with a lot of the good tools to be able to monitor and actually track what's going on and remedy issues, with the final step being that through the admin interface, we added the ability to, outside of the normal schedule, just push a new copy of that job into SQS to be run immediately, or fire it synchronously so that the server node that actually got that REST API call would run that job in process on the execution thread of that servlet so that you could very easily breakpoint it and debug it. And an interesting fact, though, is that on the Shadowfall side, they actually set themselves up a little earlier by simplifying slightly on how they could configure those scheduled jobs rather than having all of the power of Spring Quartz on their hands, and actually ran the job scheduling distributed in the first place, which I think ultimately something that we'd like to pull into the mercenary backend as well. So from the scheduler side of things to score posting, once again, it's quite SQS based. We start out with in mercenary, it can actually be quite a lot of games coming in because of being on a mobile device, but because we want to actually store all your community data and be able to show it to you on your web profile. You can actually be offline for a matter of days or weeks and playing campaign missions, and each mission is stored individually. We don't aggregate them together because then you'd lose a lot of the detail in what you did. So Scorepost comes in with a lot of games, goes into the REST API, and they're split up so that each individual multiplayer game round or campaign mission that you played since the last push gets put in as a separate job in SQS. And that game job's SQS queue is being read by a separate set of listeners to what we use for the scheduled job listeners. And the first action on receipt of those jobs is that they're pulled off the queue and we write an entry into the user's game history, and that goes into Dynamo. Now, it's a transactional write within the context of that one Dynamo table. But then we have individual listeners. When that write has completed, a number of listeners are kicked off in parallel for a lot of secondary jobs that happen as a result of each game Scorepost. So we update stats because we're quite keen on our analytics and we want to actually track our game balancing, and that ends up in another SQS queue. We also write into a number of services a numeric profile for efficient tracking of your overall scores, stat history so we can get a time series graph of what you've been doing, leaderboard service, does what it says on the tin, and then a few other things such as valor leaderboards, profiles, badges, that kind of stuff. But all of those secondary jobs have a nasty side effect of how they fail. If the original game history write fails, then you get an exception that throws up to the SQS receiver, and it doesn't actually confirm that message in SQS, so it would get represented. If the secondary jobs fail to run, though, particularly if some of them fail to run, there isn't a good way to recover that in the system as we originally wrote it. And as we found when we actually had our Dynamo tables accidentally reconfigured in production to 5 reads and 5 writes per second, and we're getting a lot of those failure cases, we had a situation where when you looked at your profile on the web, you had one total score when you looked at it on the time series graph, a totally different one when you looked at it on the profile, and a third different value for your overall score when you looked at it on the leaderboards. And this was clearly a big problem. That's a bit of an understatement. Nothing so angry as a user community whose stats don't add up. But what we then did, and we could do this very quickly, and I can't understate how long this would have taken us in the old architecture, we actually just rejigged things a little so that the listeners on those game history jobs, instead of actually trying to do those secondary jobs, they just punted another message into yet another SQS queue. So for every Scorepost that went in, you'd actually have 7 or 8 messages being punted into SQS, with SQS quite happy to handle that extra load. And then each one of those jobs is processed by another set of receivers and executors, and when they fail, if you're having issues with your backend, then the failure state for those is that they can be retried. They will still sit in SQS until they're actually confirmed and removed from the system. And you've got all the nice CloudWatch monitoring data points that you get with SQS, so you can tell when your queue's going horribly wrong because of the jobs not being processed. And we've actually also got all the job management stuff in those receiver threads so that we can see which elements are going wrong. And if we've got particular services which are going horribly wrong, we can actually split things out further in a very short process such that you can actually run something like the numeric profile update into its own queue just for that. Also, as a developer, we have the nice little sneaky thing that we can go in, use the AWS console, and just have a quick peek at what messages are in the queue to see what's going on, to see if there's any particular pattern about the messages that keep being represented, without actually causing any destructive behavior on the queue. But by doing this and actually having another set of receivers, we resolved that kind of unrecoverable error state within the system. Would have been nicer if you hadn't put the error state in the first place. And then finally here on the leaderboard side of things, a few people have mentioned leaderboards through the last couple of days. We actually implemented a leaderboard component originally on SimpleDB, which was simple and straightforward. And quite slow though. So as soon as DynamoDB came out, we actually ran really quickly to translate that implementation over to DynamoDB so that we could actually swap out our components very easily. And in fact, we actually ran for a little while mirrored with both Leaderboard backends running in dev, not only so that we could actually mirror the data across, but also so that we could actually just validate the performance was how we expected it. However, the downside to going to Dynamo was that we couldn't use a simple one-table structure for our leaderboards. We had to actually have a secondary table for all of the sort columns. So if you've got a leaderboard sorted on, I don't know, shots, hits, accuracy, points, kills, deaths, dozens of other things, for each one of those sort columns, you actually have to have an extra row in the leaderboard sort table for every row on the main table. So you actually get quite a lot of bloat on that leaderboard table. And there's actually some transactionality issues here when you do updates, because with each write and each update on the leaderboard being usually one read and one write onto the main table, and then a delete of the old value in the sorted view, and then a write to add the new value in so that you can actually scan through using range queries within Dynamo to look at the sorted view. You've got problems where if the instance gets terminated halfway through that job, you can actually have the delete been done on the secondary table, but not the insert. And also with eventual consistency on the reads of the leaderboard views, even if nothing had go wrong, there were short times when people's data is kind of in an intermediate state of being updated on that secondary table. So we had to have systems where we resolved user scores appearing twice temporarily when they'd actually just upped their score a little bit. But the eventual consistency view of that leaderboard showed both of the values at the same time, even though the delete had gone through and the write had gone through of the new data. We also tried out various things with single table versus multiple table implementations. One nice thing you can do with Dynamo, which is very kind of anti the old SQL view, where DBAs really don't like you deleting SQL tables at runtime. If you've got a daily or a weekly leaderboard, if you actually have your leaderboard structured so that each leaderboard is in its own table, you can actually purge out last week's data very easily just by deleting a table. Whereas if you've got everything stored in a single table, you might have 100,000 rows of data stored in that leaderboard from the last couple of days, and deleting it then is a lot of reads to actually scan through that data on a range query, and a lot of deletes. So actually using multiple tables can be quite handy for that. On the other hand, operationally, dynamically creating tables is still a bit of a problem if you want to be able to back up your data. And finally, with the leaderboards, we still had the issue that we had way back on the SQL side of things and never really got away from, which is that fast ranking is still a problem. So you can find your scores on the leaderboard through a one-read operation. You can page through the leaderboard via any of the sorted columns very easily. But actually finding out what rank you are, well, you can actually count how many read operations that's going to cost, because if you use the simple size operation on a range query, that is quite clearly going to be reading through all the table entries above your score. And in fact, whilst that is more obvious when you're using something like Dynamo or SimpleDB, actually, often a lot of the same operation is going on in your SQL database when you try and do a rank query. But that doesn't show up when you're doing dev with small volumes of data, but when you're in production, and if you're like me and you're 100,000th in the overall leaderboard and not in the top 10, it's quite an intensive operation to find your kind of perfect rank within the system. So for that, we actually implemented a couple of different ways to get around that problem. If you want to know more details, you'll have to ask me later because it's a big and fussy topic. But we had a fast ranking component which used a reverse index that we'd calculate and update on the fly as people's scores came in. So that would actually give you a table which ranked through from score to rank. And we also had a statistical predictor that would periodically, on a scheduled job, scan through all of the leaderboards and actually generate a curve on a number of control points. So if you had a 100,000 row leaderboard, it might actually compute 100 control points to be able to predict what rank you'd have for a given score. But each of those ones has its own pros and cons, and neither of them is a perfect answer to the fast ranking problem that we have. So from those few specific examples, you'll see how we actually made use of AWS services a little bit, and also from the overall topology, how we made use of the kind of application level services. But we did have a number of issues. First of all, very quickly, old style monitoring. Within Sony have got a network operations center, they've got their own monitoring tools, and they've got people in there 24/7. And initially how we set things up, there is actually monitoring on each individual server instance on these auto-scaled servers. What we found very rapidly was that with the topology only being updated maybe every 15 minutes of those auto-scaled environments, oftentimes the old school monitoring systems would actually throw up a bunch of red lights. Oh my God, that server's gone horribly wrong. Well, no, actually the autoscaler terminated it 10 minutes ago. You haven't updated your topology yet. So I'm very keen on something that was being mentioned yesterday around getting away from monitoring individual instances. So as well as monitoring the built-in things like SQS queues, monitoring ELB latency on your overall REST APIs. We also have a lot of more detailed custom CloudWatch endpoints where we actually are monitoring things like how long are the leaderboard requests taking to get answered, how long is it taking to log in, all those kind of things, and then drilling into the underlying services. So we've got that same kind of onion skin that we can look into what's going on in the system, whereas the old style monitoring was often a source of unneeded callouts. We also had automatic scaling of server instances, but manual scaling management of DynamoDB, which resulted in, how can I put this? Me running as a bot when we were in beta, going through the hosting guys and looking at the CloudWatch metrics for all our Dynamo tables and doing this kind of head-scratching, chin-scratching exercise. Do we need another 50, 100 reads on that table? And I think it only took us a couple of 3 days to realize that this was a really stupid way of doing things. And so what we actually implemented then was another scheduled job on the game servers that we've been quite hesitant to turn on fully, but which in a scheduled job looks at each table, looks at the CloudWatch metrics, does in a piece of code what we were doing manually and being kind of bot-like. And that actually increases the throughput during the day. And then once a day, it will decrease it, because with DynamoDB, whilst you have got some auto-scaling capabilities there, if you use them, you can't actually just freely scale things up and down constantly. You can only do, I think, 4 down scales per day. But that gives us a certain amount of distance from the day-to-day grunt work of managing our DynamoDB tables. But with a little bit of configuration around it, we can actually automate that. We also have a problem with DynamoDB and the leaderboards. We have a few, actually. First of all, we predated the local secondary indexes feature and had already implemented our leaderboards when that came in. We did look at actually switching over to using local secondary indices, but I think some of our tables, the number of rows and the number of attributes and the weather in Alaska combined together to work out how much volume of data there was going to be in that table was going to be above the limit of what we could have used with a single hash key, which is limited to, I think, 10 gig of data overall. So we had to stick with that existing system. And also with our leaderboards, not all leaderboards are as active as each other. With Killzone Shadowfall, you've got user-generated game modes that users can create a new custom game mode, and each game mode has its own leaderboard. But also you've got developer-created game modes that are in there from the start. And the activity level on those ones is much, much higher than you're going to see on the user-generated ones, where a lot of those game modes will be only played a few times. And the problem with those actually all being in the same DynamoDB tables is that you have a number of hash keys which are active like orders of magnitude higher than others. And that leads to hotspots in that DynamoDB table. And so you have to kind of over-provision the throughput quite a lot to scale up the shards that underlie the DynamoDB service that are providing access to those particular hash keys. And whilst we tried looking at whether we could split those out into separate instances of the leaderboard service, it actually turns out that it's not that simple from the game point of view, because post-launch, some users will create game modes that everyone loves and that will be recommended, and they're on the front page. So it's not like we can actually just statically configure one table for the really popular leaderboards and another table for the kind of general run-of-the-mill leaderboards. Those things would have to actually be dynamically moved from one set of data to another, and we haven't actually yet resolved that issue, so we're just having to monitor very carefully the status of those tables. We also have problems with surprise changes to the console. We've gone from a land where we had control, we had to build our own deployment systems and all our monitoring systems and everything, but now we use AWS console. And that's great until the day comes when the Beanstalk pages all change to a wonderful new UI, and the CloudWatch pages all change again. And whilst for us as developers, that's not such a bad problem, because it only takes a half an hour to get your head around the change. But one of the other titles that we work with, they just implemented a runbook so the network operations guys could actually restart servers and play around with configs and things like that at 2 in the morning without waking up the game team. And that included a whole load of detailed information on what was where on the AWS console and what to change. And then within a couple of days of their title coming out and the runbook being published out to the NOC, those Beanstalk pages changed completely. And so they had to rewrite their runbook. And you're taking away a certain amount of control because you're no longer actually owning that system. That is somebody else's system. And it would be lovely if we could actually opt into those updates. You know, give us a month to pick up the new version. But as it stands, you sometimes get a strange call from a NOC guy who can't actually make the changes themselves because they're not entirely sure of how the system works anymore. And finally, we hit some limits of CloudFormation. We had these hybrid deployments that couldn't just use CloudFormation on their own, but we also had some things with Beanstalk particularly, where some of those CloudFormation resources aren't updatable currently. So if you're trying to follow a best practice of you deploy using CloudFormation, you reconfigure using CloudFormation, you update the web app version using CloudFormation, you can't do that. So if you have a disaster recovery situation where you want to deploy to a new region very quickly, if you use the CloudFormation template that's currently in prod and redeploy that to a new region, you actually end up deploying the servers from, if you're lucky, a couple of weeks ago, but it could be months. So we're actually quite keen to see updates on the CloudFormation side such that we can actually update those elements and keep to kind of, I hate to say the word enterprise, but I think it's an enterprise best practice. Overall, though, I think we have actually learned some pretty good lessons. We've moved from SQL to NoSQL, and there's been some road bumps along the way, such as with the score management side of things, but it's actually allowed us to get that flexibility we never had before. And actually having that flexibility, added options, we had some late decisions from the game design to add in new features on Mercenary, and we could actually add whole new services in ways we couldn't do before. Also, as I mentioned with the DynamoDB, the dynamic scaling and management, which gives you resilient scaling and management, doesn't stop at just server boxes. You have to look at everything that's in your server stack and everything you're dependent on. A lot of the AWS services manage that scaling and manage that resiliency without you needing to look at them, but not everything. So you have to actually appreciate everything in your topology. And finally, we've still not found a silver bullet for leaderboards. I'm quite keen. We do use Elasticache and Memcache at the moment, but I'm very keen to look into Redis and some of the in-memory solutions for leaderboard management. And maybe we'll swap out post-launch to a faster leaderboard solution and one which doesn't hit the Dynamo side quite so heavily because we have to have some quite high throughputs configured on Dynamo. And like I say, we've also got that hotspot issue. Overall, though, I think we have actually transitioned to a much more flexible system and one that we've implemented using smaller teams than we've had before. I've got a few minutes now for any questions if you've got any.